Good evening. I am Sungbin, Chair of Quantum and Introductory Seminar Manager of QISCA. It is my pleasure to introduce today's introductory seminar speaker, Sungbin Lee from SQRT. Well, we are all familiar with Sungbin Lee. Sungbin Lee is the president of QISCA and a senior in the Department of Physics and Astronomy at Seoul National University. He currently has interest in quantum circuit simulation using tensor networks. Today, he will be presenting a talk titled Introduction to Tensor Networks, sharing insights from the paper, The Density Matrix Renormalization Group in the Age of Matrix Product States by Ulrich Schollwöck. Please welcome Sungbin Lee to the presentation.
Okay, thank you for your kind introduction. Can you hear me?
Yes, we can hear you.
Okay, so my name is Sungbin Lee. I'm the senior undergraduate student at Department of Physics and Astronomy at Seoul National University. And today I'm going to introduce about the basic concepts of tensor networks, the density matrix renormalization group, and what we can do with DMRG algorithms. So let's start with what is tensor networks. So yeah, all of this, part of my presentation slides were from my professor's lecture slides for tensor network lecture slides published in the fall 2022. So in these slides, he basically states that tensor is a multi-dimensional array. Well, that's excluding the part that there is also like, conjugate and anti-conjugate tensor classes too, but we usually do not care about those classes in quantum information's perspective. So we just use tensors as multi-dimensional array. So rank of a tensor is the number of dimension, which is the number of legs. Legs means this number of indices in these tensor network diagrams. So rank 1 tensor, which is we generally say it as a vector. We can also use dual vector as well. It doesn't really matter. It's a rank 1 tensor, so it has a single indices, meaning one leg, denoted as alpha. You can also like draw it as the square rectangular with this leg coming in. Rank matrix also represented as rank 2 tensor, has 2 legs. Rank 3 tensor has 3 legs. And actually the direction of this leg indices shows that they're either coordinate or anti-coordinate systems like vectors or dual vectors. But I'm not going to talk about vectors or dual vectors in these presentations. So in tensor network notations, we can write cat as sum of another cat times the unitary transformation, which is a matrix. So we usually write it as a rank 2 tensor. That's also the same for bras. We can also write these complex conjugate coordinate transformation matrices as a rank 2 tensor, which is also a tensor network. So we can sum over every repeated indices to mimic the matrix multiplication in this matter. So tensor network is a generalization of a tensor in a diagrammatic form, which makes computations much more easier. So you can ask, why do we have to care about tensor networks? It's because we can sort of override the exponential barrier, which presents in many quantum many-body systems. Like for instance, if we're going to compute the matrix elements, if you have this kind of tensor network diagrams, we abbreviate as matrix product states or MPS for short. If you have an MPS representation of a wave function, no matter how many qubits you have, we can exactly compute these expectation values over labs and matrix elements with polynomial computational complexity. So imagine if we're going to compute this O1, O2 time O1, O2 correlation function, the expectation value of the correlation function for a given given multi-dimensional wave function psi represented as a matrix product state, which is one of the tensor networks. So if we have access to the matrix product representation of this wave function, then we can compute this expectation value polynomially independent of the number of qubits. Like for instance, if we have 5 qubits here, like 1, 2, 3, 4, 5, then we can just compute the indices one by one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if computational costs both time and space complexity is polynomial. Since we only need to keep these individual tensors and contract them using zippers. So we first zip these two tensors here, then these 4 and 5 tensors, including the expectation value. Then compute 2 more tensors, compute 3 more, and 2 more. So the number of tensors you need to compute in every series is independent of the number of qubits you have. So we can actually compute the exact expectation values independent of how large your wave function is. So that's the key advantage of tensor networks. You can compute seemingly exponentially large physical observables in polynomial time complexity. And that's one of the crucial part of quantum many-body physics and also for quantum computations. So we can also represent left and right normalized tensors. They're defined as if you contract the left indices of a matrix product space, it becomes the identity. So we can basically ignore the left part in this MPS. That's what you call the left normalized tensors. We can always make a left normalized tensors because if you perform the single level decomposition, SVD for short, then we always get the left isometry tensors. Left isometry tensors are, by definition, left normalized because if you construct in the left manner, then it becomes the identity. So apply this left normalized tensors to the generalized matrix elements of Hamiltonian. Then we can compute these Hamiltonian elements by just contracting the entire left part as isometry, which is basically just identity. So we can compute all of these tensors indices from 1 to L minus 1 and contract them trivially because they're identity. So we only need to compute the values from L to N. We can exclude all of this L part. So if we sum it over all of the every possible L indices, then we can get the matrix elements of the entire Hamiltonian. So that's the key reason why we use tensor networks to compute physical observables that seems to pose exponential barriers for exact computation. Then you can ask, but do we have but this all means but this is all useful only if you have MPS representation of the wave function. We have to have this kind of representation for this psi to compute all of this matter. And the answer is yes, but there's a canonical way how we can obtain these MPS representations up to a certain error bounds. And that's called the canonical form of MPS. So every wave function is normalized. Like the norm of the wave function has to be always be 1. Because if you sum up the entire probability of a system, it is 1. That's same as the unitary evolution of importance in quantum mechanics. So we can always define the canonical form of MPS. As I told you before, this indices represents the left normalized tensors. So if you construct them in a left manner, they'll always be identity. So if you construct this left conical MPS with this complex conjugate version, if you construct all of this matter, it becomes the identity, then also identity, all the way to the part until it becomes 1. Because actually at the final part, there will be no tensor indices because there will be no more qubits. So number of indices is just 1. We call this a dummy leg. Basically means not important leg. And if you take a trace of a dummy leg indices, it is always 1. So if you perform the singular decomposition in all of the manners for every qubit order, you can get the canonical form of MPS as a representation of a given wave function. And that generally will be exponentially hard to compute because singular decomposition scales as the third order of the number of qubits. However, during the SVD, we can truncate the bond dimensions up to a certain level to obtain the approximate representation of a given state psi of the given wave function, many-body wave function. So there's a trade-off between the accuracy and the computational complexity. Obviously, if you're going to obtain a general representation of a general many-body wave function, that would be exponentially hard. But for certain problems, like the ground state of the given Hamiltonian, of the gapless Hamiltonian, generally the entanglement entropy is not infinite, even for infinite and infinite number limit. So we can generally obtain a good approximation of the MPS representation for those problems, for those many-body problems. And that's why we use MPS as a tool in condensed matter physics to discover the ground state of the given Hamiltonian, to compute its physically observables, to discover the phases, draw the phase diagrams, and classify the phases of matter. So that's one way you can use MPS as a tool in condensed matter physics. So as I said you before, one way to use MPS usefully is to make the ground state representation in an MPS form. But to do that, we also have to obtain the tensor network representation of a Hamiltonian. Because to construct the MPS efficiently, all of these physical observables has to also be represented in the tensor network diagram. So there's a general way how we can represent Hamiltonians as a tensor network representation. So for instance, let's consider a transverse field Ising model. So there is a one-dimensional transverse field Ising model where there is a coupling term J that couples the nearest neighbor spins SL and SL plus 1. And there is the magnetic term H, which sums up the every spin values their direction in the Z direction. So we can generally make the Hamiltonian the MPO representation of this kind of spin Hamiltonians. Like for single site operators, we just need to like sum up every spin operators in the L indices for all of the L sites from 1 to n. So this is the MPO representation of this magnetic field term. So in more generally, we can represent Hamiltonians also in this MPO form. MPO stands for matrix product operators. So state, we can represent it as matrix product states. Hamiltonian, which is a unitary matrix, which is a unitary operator, can also be represented as a matrix product operators in this manner. So MPO is generally a 4-rank tensor. There's 4 legs, 1, 2, 3, 4. But we cannot draw 4-rank tensors in our brain or in the paper. So we usually represent as a 2-dimensional matrix where there is the 2 indices crammed into a single dimension. So this row dimension stands for 1 and 2. I'm sorry, for alpha 3 and alpha 4. So if we construct alpha 3 as 1 and 2, so this dimension is 2. Alpha 3 dimension 1 represents this alpha 1, which is also rank 2, which is also a 1 dimension 2 tensor. So all of this is 2 by 2 by 2 by 2 matrix. So that can represent as a 4 by 4 matrix because 4 by 4 equals 16, 2 by 2 by 2 by 2 also equals 16. So if we impute alpha 3 indices, contract them as 1, then we get this 3-rank tensor, which is 2 by 4 tensor. If you also contract alpha 4, which is a 4th leg in this direction, contract it to 1, then we get a 2 by 2 tensor, where only 1 and 2 indices is left. So this is how MPO is represented as a 2-dimensional matrix. So there will be 2 times 2 matrices, all of them crammed into a 4 by 4 matrix. So if alpha 3 and alpha 4 is both 1, we get a 1, 0, 0, 1 matrix. If alpha 3 is 1 and alpha 4 is 2, we get the trivial 0 tensor. If alpha 3 is 2 and alpha 4 is 1, we get the Hamiltonian times the spin matrix. And we also get the identity matrix when alpha 3 and alpha 4 is both 1. Both 2. So if we multiply these MPO matrices in a 3 and 4, if you contract the nearest neighbors MPOs in 3 and 4 direction, like contract in the 3 and 4 direction, then it's just a normal matrix product. So we can just multiply the matrix product states. So if you multiply this MPO with the nearest neighbor this MPO, then we get just a normal matrix product. So we get this kind of Hamiltonian, which is exactly the same as this Hamiltonian, the single site operator term. So in short, this MPO represents the MPO representation of this single site part of this Hamiltonian. So if you multiply this MPO n times, it's same as representing this Hamiltonian for n-qubit systems. So that's how we make the MPO representation of a Hamiltonian. We can also do similar stuff for nearest neighbor interactions like this term here. If we define the MPO operators in this manner. So for this case, this MPO is a 2 by 2 by 3 by 3 MPO, 3 matrices. So if you compute this nearest neighboring 2 MPOs, then it's also same as contracting it in the matrix product operators. So we get this kind of nearest neighbor interaction terms in the Hamiltonian. So if you contract the n leg dimensions and the first leg dimensions for both 1 and 3, then we will get only this part left, which is exactly the same as the nearest neighbor interaction terms in this Heisenberg Hamiltonian. So in short, we can make a tensor network representation of a Hamiltonian that fits well with this MPS representation of the many-body wave function. Combined together, we can compute the matrix elements of Hamiltonian, as well as the ground state energy, and also get the ground states of a given many-body Hamiltonian that we cannot generally solve with our hands. So it's a numerical tool in computing the ground states of a Hamiltonian. That's not the only thing what MPS can do. It is one of the most well-studied cases that is important in physics. So, as for now, I'll introduce what is the DMRG, which stands for Density Matrix Renormalization Group. DMRG itself is like independent with tensor networks, but nowadays we use DMRG with tensor networks because basically the theory behind the DMRG is kind of complex, but to implement it in tensor network diagrams, then it is much more easy to compute in practice. So that was like first theorized in like 1992, not that long ago, only about 30 years ago. So the goal of DMRG is to minimize this cost function. Well, H is a Hamiltonian and psi is the MPS representation of a many-body wave function. So minimizing this is equal to getting the ground state of a given Hamiltonian H with maximum bond dimension D, obviously, because there has to be an upper bound in bond dimensions where we can compute. Obviously, for infinite sizes, the bond dimension will grow exponentially large, but we cannot compute it in general, so we have to truncate the bond dimensions up to a certain extent. So how we can perform DMRG with MPS and MPO is to iteratively minimize this cost function. How we can do this? We first define the tensor network diagram representation of the cost function, which is the linear sum of these two operators. So we contract the psi many-body wave functions and also the Hamiltonian expectation value of these many-body wave functions. So achieving minimum of this cost function is similar to achieving extrema by taking a derivatives. So taking derivatives in tensor networks is simply just like getting rid of the tensor, because that's the definition of derivative. Like is to look how much has changed if you exclude some part in the function. So this one is exactly the same as this diagram here. So optimizing the CL, which is the canonical side canonical term in the side canonical representation of MPS is exactly the same as minimizing this cost function, which is exactly the same as obtaining the ground state of the given Hamiltonian. So performing Lanczos methods by constructing this entire tensor network, which has polynomial time and space complexity, we can optimize and get the ground state of the given Hamiltonian within polynomial time complexity. Yes, it is approximate, but as I'm going to show you right now, it is a good approximate that works for many good Hamiltonians. So this is technical details on how to implement DMRG. I'm not going to explain it here. So I'll show you the real-world implementation of DMRG for these three Hamiltonian systems. The next nearest neighborhood Ising model, which has J1, J2 coupling term. The Heisenberg XXG chain, which is a sum of the two executive spins with this isometry term minus the magnetic field. And I'll finalize my presentation by showing examples of single orbital Fermi-Hubbard model, which is there's an on-site interaction term U and a chemical potential mu, which determines the electron fielding of the system. So let's start first with nearest neighbor Ising model. So this Hamiltonian can be represented as like this 2x2x 4x4 MPOs. So this is an MPO representation of this Hamiltonian. So this is the results of the ground state energy with the DMRG algorithms. So as you can see, there's nothing you can tell with this DMRG algorithms right now, with only the terms in ground state energy. But however, if you compute the expectation value, the spin magnetization and the anti-ferromagnetic spin magnetization, then we can show that this is a ferromagnetic order state and this is anti-ferromagnetic order state. And it's pretty much obvious because if J1 is above 0, then the ground state of this Hamiltonian will be the anti-ferromagnetic state, the state which perturbs with alternating spins +1 and -1. So that's for this phases. If J1 is minus, then the ground state of this given Hamiltonian has to be a ferromagnetic order, like spins all align in the same direction. But if there's a J2 term, then both J1 and J2 will have to fight each other, and J1 wins if J2 is smaller than the half of J1. That's the conclusion of our DMRC algorithms. If J2 wins, then it becomes a frustrated phase where the spin is up, up, down, down, or up, down, down, up. So as we can see, our DMRG algorithms can capture these different phases with minimal computational cost. Yeah, actually, this is a pretty much trivial model, so we move on to more complex. So this is the Heisenberg XXG chain Hamiltonian. It can be represented as an MPO, as a 5x5x2x2 MPO, like this one here. So it is known to have gapless, singlet, non-degenerate ground states with no long-range magnetic order due to Mermin-Wagner theorem. Since it is a one-dimensional system, even at 0 temperatures where only quantum fluctuation exists, there is no spontaneous symmetry breaking, so there is no long-range magnetic order. That's the theoretical part. And actually, if this delta ZZ is 1, so basically it's an isotropic Heisenberg model, and no magnetic field, no external magnetic field, and the ground state energy is given as minus 0.44315, which can be exactly solved using Bethe and such. It's 1/4 minus log 2, where log is a natural log term. So computing this ground state with Bethe and such is very hard, mathematically hard, but with DMRG algorithms, we can exactly compute this ground state energy. So this is the DMRG algorithms. It gives the minus 0.44314, which is same as the exact value up to 4 digits. So if we extrapolate the values as as a function of the number of qubits. Well, R is the number of sites. Then we can get the exact ground state value, even without using the Bethe and such. With only bond dimension 50, it only takes several minutes to compute this value. It's not that hard if you use DMRG algorithms. We can also classify phases of Heisenberg XXG chain with DMRG. So this is the ground state energy per site, and the maximum entanglement entropy, given as a function of the ZZ coupling term and the magnetic field age. So as you can see, there's two hyperparameters in this Hamiltonian. There's this isotropic term and the external magnetic field term. So there's the key differences in three phases. First, there is no entanglement in this large area. It is pretty much obvious because it is a ferromagnetic state. If delta term wins over the external magnetic field, if this external magnetic field wins, then the ground state has to be aligned in a single order for this Hamiltonian to have the ground state. So obviously there is no entanglement entropy for those situations. So that's the ferromagnetic order. But even if you have no idea what the Tomonaga-Lutingo liquid or antiferromagnetic states are, we can conclude that these two are different phases with this one because their entanglement entropy scales are clearly different from the ferromagnetic order. In condensed matter physics, we classify this term as the TLL liquid, which is basically a metal in one dimension. Since it is a metal, it is gapless. So it means currents flow, there's no gap. If this interaction term wins over the external magnetic field, then it becomes the antiferromagnetic state, which is also pretty much obvious because if this term is way much stronger than H, then we can just ignore this one. And the phases will clearly be governed by the antiferromagnetic order, though the spins are aligned in alternating direction with the axis. So our DMR's algorithm clearly shows that the strength between this isotropic ZZ term and the external magnetic field is linear because they both grow linearly. So even if you have no idea what TLL is, you can still classify those three different phases in this Hamiltonian, and they couple with each other linearly. That's also the same if you measure the order parameters. This is the ferromagnetic order, and this is the antiferromagnetic order. So this is the ferromagnetic phase, and this is the antiferromagnetic phase. But there's a different phase between, and that is a gapless Tomonaga-Lutingo liquid. Ferromagnetic and antiferromagnetic phases cannot be continuously coexist each other in this situation, so there has to be a gap closing. So there is a gapless phases between these two ferromagnetic and antiferromagnetic order. And we can clearly cite these reasons by using DMRG, by using tensor networks. I'll skip the details of this part. It's basically the same as these diagrams over here, like just plotted in graphs, classifying different phases by computing the expectation values, the entanglement entropy, and the ground state energy. It's all possible if you use tensor networks. So this is for 50 sites. You cannot compute 50 qubit systems using classical computers. It will require 2 to the power of 50 bits. You have to use a supercomputer to compute all of those. But by using tensor networks, we can exactly classify the phases without using supercomputers. So I'll move on to the final parts. That's a single orbital Fermi Hubbard model, which is by the far more complex phases than the rest of the two. So this Hubbard Hamiltonian can be represented as a 6 by 6 by 4 by 4 MPO, which is given as this MPO. This is 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And this interaction term, the Fermi Fermi excitation operators, creation annihilation operators, they are 4x4 matrices in general. If you do not use symmetry, if you use symmetry, the SU2 spin and SU2 charge symmetry, then we can further collapses the MPOs to have even smaller space overhead. But that's too complex for this seminar, so I'll just use this MPO representation. So by changing this chemical potential, we can control the filling, the electron filling of the Hubbard Hamiltonian. So it is half filling, meaning that half is filled with electrons and half is empty. When this chemical potential is half of the interaction, like if U is equal to 2 mu, then it's half filling, meaning that the average occupation is 1. So if you think of the if you think of the Pauli exclusion principle, then there can only be 0, 1, or 2 electrons at a single site. So if half filling means there's only 1 occupied electrons per site on average. And that is achieved when this Hamiltonian has a particle symmetry, when interaction term is twice the chemical potential. There's also different phases how we can classify theoretically this Fermi-Hubbard model, but I'm going to use the DMRG to classify the order. So this is the filling versus the chemical potential. Obviously, when chemical potential is half of the interaction, then it is half filling, meaning that this filling is 0, meaning that this average occupancy is 1. So if you compute the ground state energy, then obviously you can see that there is a gap at half filling. But there is no gap and it is not half filling. So it means that there will be some kind of different phases at half filling for this Fermi-Hubbard model. That's also true if you look at the interaction, if you look at the von Neumann entropy. So if you plot it in the graph, then at half filling, the ground state energy per site per interaction, there is a sudden jump. So it means that at half filling, this Fermi-Hubbard model is a mode insulator because there's the energy gap. It's the insulator at half filling. But when filling is not 0, then it is a metal, a gapless metal, because there's no gaps. That's also true for theoretically. So this is a theoretical charge gap, meaning gap of the ground state energy. For one-dimensional Fermi-Hubbard models, this is a theoretical term published in this PLL paper. By using DMRG, we can exactly compute the charge gap numerically. While this Fermi-Hubbard Hamiltonian may seem trivial, this result is non-trivial, very non-trivial, but we can still exactly calculate by using tensor networks. That's also true if you look at the terms for the spin correlations and the charge correlations. They both have alternating states, which basically shows that they are at half filling. It shows the Tolman-Luttinger liquid state, the TLO phases. And it also shows polynomial decay at half filling when the average occupancy is 0. For non-half filling states, this charge correlation decays exponentially, not polynomial. So we can classify 2 as different phases by using DMRG. So that's basically the end of my talk. The conclusion is very simple. DMRG is great. We can solve many non-trivial problems in condensed matter physics and quantum many-body states. So thank you for listening to my seminar. If you have any questions, feel free to ask.
Okay, actually, I have a question.
Okay.
And I was curious, what in the many-body quantum system, what physical assumptions must be made in order to use this tensor network calculations?
So you're saying what is the physical motivation behind representing tensor networks as a ground state of the many-body wave function?
So in order to use the
Now you're saying what are the constraints?
yeah.
Okay. So what are the conditions that our DM merger works well?
Yeah, exactly.
Yeah, okay. That's actually a very good question, but actually a very hard to answer. So in general rule of thumb, for DM merger to work well, the ground state of the given Hamiltonian has to have the area law of entanglement, not volume law. So for one-dimensional Hamiltonians, the area law generally scales as a log L. So it means the entanglement entropy of the ground state has to scale logarithmically in the number of qubits you use. So if the entanglement entropy grows not logarithmically but linearly in the number of qubits, then it is hard to represent in tensor network diagram because for MPS representations to work well, we have to contract the bond dimensions up to certain d order d. Well, d is just an integer number, because obviously we cannot let the bond dimensions to grow exponentially forever, because that will blow up our memory space. So to obtain a good representation of a ground state of a Hamiltonian, then the Hamiltonian must follow the area law of entanglement for tensor networks to work well. Then you can also ask, how can you determine whether Hamiltonian follows the area law or volume law? And actually, unfortunately, that is an NP problem. There is no general rule of thumb how we can do that. We can only do it heuristically by actually computing the ground state of the Hamiltonian and confirm whether our methods works well. We have to compute the how entanglement entropy scales as we increase the size dimensions, and if those entanglement follows the volume law, then it is very hard for classical computers to represent because there's huge entanglements. For those situations, we're going to have to use quantum computers. But actually, for many Hamiltonian systems, like Heisenberg chain or Fermi-Hubbard models, tensor networks works well. So we can say that it is a good method that works well for many Hamiltonians that has the area law of entanglement ground state. Is that a good answer for your question?
Yeah, thank you. Yeah.
Okay. Any more questions?
더 질문이 있습니다.
Okay.
그 인테그먼트 엔트로피는 텐서 네트워크에서 계산을 어떻게 하는지 그리고 뭐 계산 복잡도는 어떻게 되는지 궁금합니다.
Okay, so you're saying the von Neumann entropy calculation computational costs? And to answer your question, there's no computational overhead in computing the von Neumann entropy.
뭐 폴리노미얼 복잡도인가요?
Yes, it's polynomial because if you think of the canonical form of our MPSs, so this is the canonical form, the bond canonical form, then this bond tensor represents the singularly decomposition in our Schmidt coefficients. So this bond tensor is a Schmidt coefficient tensor. So if you can obtain this tensor, we can compute the von Neumann entropy between bipartition A and B. So computing this bond tensor is same as just obtaining the canonical form of the MPS, which is what we always do when computing the ground state energy.
그러면은
So it's about the same as just getting the MPS representation.
바이팔티 서브시스템으로 그 구조만 계산을 할 수 있는 건가요? 아니면은 이 사이트를 떨어진 걸 다 이렇게 잡았을 때도 그런 서브시스템도 할 수 있는 건가요?
So it means what happens if you have bipartition A in like this, and B, and this one?
뭐 예.
Generally, so for one-dimensional wave functions, to compute those bipartitions, then you have to first perform the sort gate to make them align in left and right part.
아, 그럼
네.
수학 다 온라인에 해놓고
Yeah.
한다. 알겠습니다. 또 하나 질문이 있는데
Okay.
이 텐서 네트워크를 이용해서 그라운드 스테이트랑 페이즈를 예측을 한 다음에 그걸 바탕으로 실제 실험으로도 뭔가 그러니까 실험적 시스템에서 그런 거 확인하는 뭔가 그런 연구들이 좀 있었나요? 궁금해서
Yes.
보기
Yes,
싫어서.
there is. Actually, there are more computational methods how you can compute the ground state. There are also methods like exact diagonalization and the quantum Monte Carlo, QMC. And there's also numerical renormalization group NRG, which is basically what the previous lecturer speak in last week, I guess. So you have to we can compare between those two. And we can also compare whether they're with our experimental data. Like for instance, one of our members in my professor's group recently published article. I'm sorry, not published. It's just listed in archive. In the meantime, he developed whether how the non-trivial superconductivity arises from the MATBG, the magic angle twisted bilayer graphene, when the filling is above or below 2. Actually, there's experimental data on the gap closing for those situations, and he numerically like re-estimated those gap closing by manufacturing the Hamiltonian carefully and using tensor networks DMRG and numerical RG as a tool for obtaining the ground state energy and computing the charge gaps. Also computing the band diagrams and like density of states, the DOS. So yeah, there are many results on comparing the DMRG results with different methods, with the different computational methods, and also with experimental data.
그럼 마지막으로 궁금한 게
Okay.
텐서 네트워크가 그라운드 스테이트 에너지 계산하는데 이용하고 그러한 그라운드 스테이트가 에리알러의 볼륨 그러니까 인텐글먼트를 가질 때 이제 근사가 잘 통한다라는 건데
Yes.
실제 실험적으로 그라운드 스테이트가 볼륨러인 그런 케이스가 좀 있나요?
Yeah. Random quantum circuits are volume law. All
음,
random states are volume law.
그게 볼륨러인 건 아는데 그러니까
Yeah.
해밀토니안의 그라운드 스테이트가 이제 볼륨러 인텐글먼트로 주어지는 그런 경우가
Well, I'm not certain about that. I need to have, because I usually do not research by Hamiltonian. I usually focus more on quantum circuits. But there are many ways, but there are many examples of a volume law states, like all random states or random quantum circuits. So representing those in tensor networks is a non-trivial problem. Like there are also like recent studies shows that maybe neural networks can represent volume law states, but we are not certain about that.
네,
So yeah, discovering volume law states remains a non-trivial problem in both condensed matter physics and quantum like information scientists.
네. 질문 여기까지 하겠습니다. 감사합니다.
Okay, thank you. Any more questions?
Yeah, I have a simple question.
Okay.
So for the novice, could you briefly like describe what's the actual computational, like the source of like the computational advantage of tensor networks? So
Computational advantage.
I get that you can like graphically describe Hamiltonians,
Okay.
but obviously when we like code the actual model, these graphical like representations aren't actually used. So I was just wondering intuitively, what is the source of the computational advantage of the tensor network representation?
So computational advantage comes from that you can decompose the large tensors into small parts. You can decompose them.
So why does that like result in a computational advantage?
Because if you're going to like multiply like between two large tensors, you first have to have those two large tensors. And generally, the memory cost scales exponentially, like 2 to the n, if you have n qubits.
Okay.
But if we decompose them into n different small tensors, then generally the memory will scale only linearly in number of n, because we have n different parts. So decomposition generally generally overcomes computational overhead and computes exponential barriers. So to avoid exponential barriers, you have to decompose the large tensors into small ones. You have to do it in a clever way that the decomposed small tensors are still a good representation of the large one. It is approximate, obviously, but it has to be a good approximation. And tensor networks provides a systematic way of how to decompose large tensors into small ones.
So is there anything else we can do to reduce the computational cost other than just simply representing the large tensors into smaller ones? Is there anything else we can do?
Anything else you can do?
Yeah. Or is that just basically like the gist of it? Is there anything else we can do?
Yeah, other methods like metropolis sampling or quantum Monte Carlo. Like for Monte Carlo, we use Monte Carlo algorithms to sample from a large set. So how we do it? Monte Carlo algorithms basically just compute how certain that the given outcome can change. So if that probability is large, we basically guarantee that those change part is a true one, and we sample from that. If that probability is small, then we just sample from the entire set according to that probability. So there's also many other ways how we can like get like so to say non-trivial values from an seemingly exponentially large set. But how to do that generally in a clever way is a very hard problem. Actually, one of the core problems in computational science and statistics, also in condensed matter physics. But generally for quantum systems that has area law of entanglement, which means that entanglements are not too large, then tensor networks works very well in those situations. We can also do other methods like neural networks, also used in artificial intelligence. Neural networks is also the set of networks, like networks of tensors. It is not tensor networks, but it is somewhat similar in this manner to decompose every layers into different tensors and to compute them. So for computations to work well, we first have to decompose them, because there's nothing you can do. Because there's nothing we can deal with the bulk tensor.
So in essence, what you're saying is that if I wanted to create my own basic like tensor network approximation, I would just have to find a clever way of representing a large tensor and a clever way of sampling from those tensors. Am I
Yes,
correct?
right. Yeah, that's
Okay.
correct. So MPS is one of the examples, but there are many other ways you can do it.
So MPS is basically just like the simplest way you could decompose a tensor into
Yes,
lots of
right.
small
Yeah,
tensors.
right.
Okay.
Yeah,
That makes sense.
exactly. Any more questions? I believe,
Okay, yeah.
yeah, one in the chat. Like, what is this? Area law for one-dimensional quantum systems. Ah, okay. Okay, thank you for your paper. Yeah, but generally determining whether the Hamiltonian is gap or gapless, or whether it is area law or volume law is very hard. Like it is an NP problem. It is proven to be NP hard. So it's not computationally trivial. But there's still a way how you can do it. For some problems, for some classes. Not all of them, but for some of them. And actually classifying what is that sum of, what is that subportion, well, we can do it. It's still an open question that we have to answer. So if there's no more questions, then I guess I can end my seminar on tensor networks as this. So thank you for listening to my seminar.
Okay, thank you for the great presentation, and we'll move on to our Jira Club session. Thank you.